Section 1.1, Variables. So, as far as mathematics is concerned, a variable is an unknown, but we can have unknown constants as well. So the main thing we want to know with variable is that it might have more than one value. And as we hopefully remember, we usually represent it with a letter of the alphabet, for example, X, but we can represent it with pretty much any symbol we want. Here's an example where we're using an empty box. We generally want to avoid a number because that can be confusing, but we certainly could use whole words or other symbols if we need to. So you'll notice a lot of questions we might just have some sort of expression like number, and in that case, when we write it out, we will then usually give it a label, by which I mean usually a letter, and that is for making easy mathematical equations. And then of course, when we get into coding, programming, that is also something we need to do there, is making that label. So let's take an example and write this following sentence formally and with at least one variable. So the first one, are there numbers, you'll notice it's plural, so we'll need at least two, with the property that the sum of their squares equals the square of their sum. Now if you look at our options, we've got a couple of them. They all have the same mathematical equation. What we'd like to focus on now is the part that comes before that. So we could say, are there numbers a and b with the property that? Are there numbers a and b such that? Do there exist any numbers a and b such that? So as you can see, there are a number of ways that we could express this. And again, that mathematical part is remaining the same for each of them. So similarly, given any real number, its square is non-negative. And you'll notice that non-negative we could either write in English or write as greater than or equal to 0. And again, we could phrase it, given any real number r, for any real number r, for every real number r. So right now, what we want to know is all of these things are different ways to phrase the exact same idea. All right, let's hit some important mathematical statements. And we've got three in particular. The first is the universal statement. And this is when we're going to see that word all or every. So this is saying it is true of all of them. Now you'll notice it's not necessarily all numbers. Here we've qualified it as all positive numbers, but since we still see that word all, this is a universal statement. My next one is a conditional statement, and this is when we'll see the if-then structure. And right now I don't care about the rest of the problem, just that it's got the if and then the then. Our final type of statement is an existential statement. Think of it as a statement of existence. So you'll see there is or there exists. One distinction I want to note is that the universal means it has to be true for every number that we've said it works for. So there can't be even one number where it doesn't work. Whereas existential, there only has to be one. There might be more than one, but there only has to be the one. So sometimes it can be a little hard to see the difference between those two, but that's what we want to keep in mind when we see that type of problem. All right, so let's try looking at combining these. So let's try combining universal and conditional statements. So if you look at my initial statement here for every animal A, if A is a dog, then A is a mammal. We've got the for every, so there's my universal. And then we've got the if and then. Now, for a problem like this, we know that mammals are animals, so this would be an example where we don't actually have to say the for every animal A, because it is inferred from the rest of what we have. But there might be problems where we do have to explicitly write out the for every. Again, in this particular case, you don't necessarily have to write that. All right, so let's take some examples. I've got a universal conditional statement, and I'd like to find a way to rewrite it. So our initial one, for every real number x, if x is non-zero, then x squared is positive. Here are some ways we could rewrite it. If a real number is non-zero, then its square is positive. For every non-zero real number x squared is positive. If x is a non-zero real number, then x squared is positive. The square of any non-zero real number is positive. And finally, all non-zero real numbers have squares that are positive. Now, some of these might be better than others, but again, at this point, what we want to get out of this is that these are just all different ways of expressing the same statement. All right, let's look at some universal existential statements. So that means the universal part will come first, and the existential part will come second. So here, you can see we've got every real number, so there's the universal part. And this is a little bit subtle, but you'll notice has an additive inverse, so a single additive inverse, and that is the existential part of this statement. Again, for a lot of these statements, we've got more than one way to write it. We could also say all real numbers have additive inverses. For every real number r, there is an additive inverse for r. For every real number r, there is a real number s, such that s is an additive inverse for r. Again, we'll talk later about which ones might be better than others, but again, for now, these are just different ways of expressing the same thing. And generally speaking, when we talk about what's better, we want something that is relatively short, although sometimes we have to say more, but we also want to be unambiguous. We want to be very clear so that everybody who sees it is going to understand it in the exact same way. All right, let's try a few more. My initial statement, every pot has a lid. So again, here's three ways I could phrase it. All pots have lids. For every pot P, there is a lid for P. And for every pot P, there is a lid L such that L is a lid for P. All right, now what we were looking at were universal existential. Now let's look at existential universal. So these are going the other direction. The existential part is first. So if we look at our example here, there is, that's my existential part, a positive integer that is less than or equal to every positive integer. So that every is my universal part of this statement. Again, there's a lot of different ways we could phrase this. We could say some positive integer is less than or equal to every positive integer. There is a positive integer m that is less than or equal to every positive integer. There is a positive integer m such that every positive integer is greater than or equal to m. And finally, there is a positive integer m with the property that for every positive integer n, m is less than or equal to n. Again, these are all saying the exact same thing. So let's take an example and do that rewrite. So here's my initial statement. There is a person in my class who is at least as old as every person in my class. Again, here's the existential part at the beginning, and here's the universal part later. So ways we could phrase it is some person in my class is at least as old as every person in my class. There is a person P in my class such that P is at least as old as every person in my class. And there is a person P in my class with the property that for every person Q in my class, P is at least as old as Q. And again, all of those statements are different ways to say the exact same thing. Finally, we've seen problems that have just one of each of these. We've seen a few examples that have two of them. It is even possible to need all three of these. So the universal, the existential, and the conditional. Here's an example where we'll see that. Here I've got A1, A2, A3, and so on as a sequence. Now if you don't know what that means, that's okay. I'm not concerned with that part. But I'm going to read this definition. For every, there's my universal. positive real number epsilon. There's my existential, is an integer n such that for every, so here's another universal, integer n, and finally here's my conditional, if n greater than n, then that following statement. So for now, we want to be able to identify existential, universal, and conditional, and we want to practice different ways of expressing these same statements.